Short lecture. Like I said, after today, we're gonna move on to, we're gonna start getting into molecular orbital theory, right? Which is where we'll talk about all that, but it essentially has to do with where you place electrons. Okay, we're gonna talk about that. We talked about how to find valence electrons. Now we're gonna talk about where they're at. That'll kick off next week. But for now, we're talking about, and I would be taking notes. That's a good idea. We're going to talk about solutions, okay? And it ties into the lab and why the lab formed crystals, right? Because we heated something up, dissolved something in it, cooled it down, and got crystal formation. And the question is why? And we're going to explain that today, all right? So a solution, what is it? Very simply put, solution is just a mixture of two or more compounds. It can exist in all different states of matter. Typically, when you're talking about a solution, you're going to be talking about a liquid and a solid, right? That's not up here. These talk about the homogeneous, meaning same, right? So homogeneous matters, states of matter. So solids, an example of that's, you don't have to know what consists of brass, right? But it's copper and zinc, right? That would technically be a solution. You have liquid solutions, if I were to mix something like hydrochloric acid with water. And then you have gaseous solutions, which the atmosphere that we're breathing in, walking around in, that is a solution, right? Because there's oxygen, nitrogen, CO2, all that stuff's floating around us, right? So just know that there's different types, and like I said, you can have a combination, you can have liquid and solid. You're not really going to see things like gas and solid. It's not really going to be a solution that you see. It's pretty hard to get a solid to dissolve in the air, right? Good on that? Okay. So when we're talking about a solution, we're talking about two components. We have a solvent and a solute. I'll give you another definition than just what's on the screen. A solvent is a compound of which there's more of, right? So what would have been the solvent for the lab that we did? What was there more of? Yeah, right. And then so the solute then, by process of elimination, would have been the what? Borax, yep. Okay, good. So we understand that. So, or you can think about it as what does the dissolving and what's being dissolved, right? The solvent does the dissolving. The solute is what is dissolved. Alright. Solvent should be a word that maybe you're familiar with. Solvent. Like, have you ever heard of when you're trying to get rid of like glue or something like that, like a real strong adhesive, you use a solvent to get rid of it, right? It dissolves the glue. That's what it's doing. Right, so you can kind of maybe use that to keep track of what's what between solute and solvent. Ideally, in an ideal mixture, an ideal solution, the solute is evenly dispersed amidst the solvent. Alright? That's ideal. That's typically how it tends to go. What we did was we created, and we're going to get into that, we created something that was not ideal. It was not evenly dispersed. Right? So ignore the gas Just ignore the side graph. As we discussed, we all kind of realize or recognize and know that it's easier to dissolve sugar in the hot water, right? If we wanted to make tea, it's easier to make it sweeter if it's hot, right? That's just something you kind of learn by messing with the world and the environment. We're going to explain why that works exactly. And that's what this graph shows. So as our temperature increases, we have this thing called solubility, which is how well, you're going to want to write this down, what solubility means. It's how well a solvent is able to dissolve something, right? To take it in. It's the capacity to which it can take in a solid. Which makes sense. As temperature goes up, so does solubility, right? According to that graph. So as we get hotter, we can dissolve more sugar. In the lab, as we got hotter, we could dissolve more borax. You have a question? Solubility? Okay. So solubility is the ability for a solvent to dissolve a solid. Yep. Does that make sense? You understand what solubility means? Okay. So when, as I talked about, it's up on the board, right? Or it's up on the projector. So supersaturated solution. When it's heated to its boiling point and as much solid as added as possible, right? We are, in essence, we talked about this, we're overloading the liquid with as much of it as we can, right? We're then cooling it, so it's supersaturated, it's holding as much as it possibly can, and then we're cooling it. So if, and this is what we did in lab, right? If we're all the way up at this peak, and we add as much solutes as we can, and then cool it, what happens to the solubility? If we're up here, and our temperature's hot, and we cool it, what happens to our solubility? It goes down, right? So we have a problem, right? We're holding more than we reasonably can. And so, when you add, and this isn't on the board, but you're going to want to write this down too, when you add what's called a nucleus site, Nucleus, a nucleus site, when you add that, you end up creating a site. A nucleus site is essentially a site for something to hold on to, okay? When you add the nucleus site, it allows it to crash out of solution. So the borax crystallized. It crashed out onto a nucleus site. Where, there's actually a couple of them in the lab that we did. Where would the two nucleosides be in the beakers that we used? The string in the bottom, right? So the string, that one's kind of an obvious one, right? Because we got formation of crystals on the string, right? We created something for it to hold on to, an imperfect surface, to where it could form. Now, why the bottom? It's a good idea. What likely happened is there's scratches and things like that at the bottom of the beakers because they're really old and they've been used a lot and they've been abused and had things stirred in them. They've created scratches which have created really small imperfections in the bottom of the beakers, and that's what allowed the crystal formation to form at the bottom. If you had a completely smooth bottom to our beakers, right, that's the one disadvantage we have to using stuff that's probably been used since the dawn of time. It's old, it's going to have scratches. If you had used one that was brand new, brand spanking new, you probably wouldn't have had any crystal formation on the bottom of the beaker at all. It would have all gone to the stream. So you can imagine what the crystals really would have looked like had you not lost some of it to the bottom of the beaker, right? And if you think, or if you were to look at your pictures on your lab reports, your write-ups, you'd probably see that the colder temps maybe didn't have more on the rope, but they probably had, or the string, but they probably had more on the bottom, right? Because why? What were we doing? What was the point to illustrate? What were you trying to illustrate in that lab with the 3 different temperatures? All 3 of them started up here, right? Room temperature got to, I don't know, we'll just, for the sake of this graph, we got to about right there, okay? And then for the sake of the fridge, we probably got to about right here. And the ice bath, we probably got all the way down to the bottom, right? So a good hypothesis for the lab write-up would have been something along the lines of, you would expect more crystal formation the colder you got. Right? That's a very lazy hypothesis. That would be a good hypothesis. Now, before I talk about why this happens, why solubility increases as temperature rises, let's talk about this. So this, which one, there's 2 up here, right? Which one of these equations would you expect to be the one that you were dealing with? Top one? No. The lab that we had done. Which one would you expect to be the lab? So if it's not the top one, obviously it's the bottom one, right? So this is borax right here. This big messy thing, okay? Borax. So that shows it dissolved in the water, and that's when it comes out. What you have up top, so borax isn't, it likely didn't get very warm, alright? But I'm going to explain something. So 8th graders did an experiment similar. Next week is where, because I need to get you guys up to snuff on some chemistry stuff that we were lacking in, right? That, in my opinion, should have been taught probably a little bit sooner, but it wasn't. So we're up to snuff to some degree. Next week we're branching off completely entirely, right? Next week is totally ICP, where you guys should be on the chemistry path, and 8th graders are going to go off and do their thing. You guys did similar labs, because I needed to explain this concept to you, something that you should have learned, right? 8th graders did this, and they made crystals. They used sodium, this is sodium acetate, okay? There's your sodium right there, and there's your acetate, all that before it. This, which side's the reactants? Left or right? Good. Which side's the products then? Okay. So, you guys got crystals to form. So did they. They separated whatever they had from the water. We see where the separation is, right? So you've got it, you've got the little dot that's showing that it's dissolved in it, and then the plus, now they're 2 separate molecules. They're completely isolated from each other. Crystal formation, right? It's a solid. What did 8th grade also get as a product? Okay. So that is what we call an exothermic reaction. Alright. I'm gonna write this down. This is something I want you to know as well. Exothermic. Heat is in the product, so it gives off heat. Right? When they did theirs, they cooled their flask, and then it crashed out of solution and got really hot again. So a little bit of a brain exercise. Can you still see the reaction a little bit on the board? So if we had our products and we wanted to get back to our reactants, right? So everything was dissolved. And this was the same case for your borax, right? How did I get the borax crystals off the bottom of the beakers? What did I do? Yeah, I got it high, right? I increased the solubility, which is what allowed it to go back in to the solvent to create a solution. Right? So when we have something that's exothermic, and we want to drive it back the other way, if it gives off heat, a lot of times what you can do is add heat to get it to go back the other direction. Okay. Now, the opposite of an exothermic reaction, for the sake of knowing it, it's called an endothermic reaction. So it means one of two things. Your reaction either gets cold, right? You can feel the temperature change as it's cold, it's absorbing energy from its surroundings, or it requires heat to be input on the reactant side, right? It's an input of heat, input of energy. Either way that works. So that's just something for you guys to know. And then the last little bit that we need to touch on is why the solubility of something increases as temperature rises. Do we know, I think I went on this tangent, do we know what heat is? Ultimately, what it's causing at a molecular level? Do we know? Yeah, exactly. It's movement. Movement of the particles, right? So, yeah, vibrations and it gets to the point where if you've got a gas, they're quite literally bouncing around the room, right? Super hot gas is just moving all over the place the particles are. They're super spread out, moving all over. That's why when we talk about states of matter, you have solid, liquid, gas, right? Solids are pretty rigid, particle movement wise, right? They maybe vibrate a little bit. Liquids, I mean, you know what a liquid is. It moves around and it confines the volume, the space of whatever the container is holding. And then the gas expands even more and the particle movement's all over the place, right? So that's why we have a melting point and a gaseous point, right? When we heat something up, we talk about that kind of thing, the states of matter. Cold isn't necessarily a concept in and of itself. Okay, cold is just a lack of heat, right? So if we freeze something, we're not adding cold to it, but rather we're removing heat from it. Okay. The concept of cold, a cold thing, isn't an addition of something; it's the taking away of something. That's why Kelvin. Remember my Kelvin ramble about how 0 Kelvin is absolutely no heat whatsoever. That's why 0 Kelvin is, because that's how heat really works. Now back to solubility. We understand that it's particle movement, right? So if I have a cold thing of water, you can imagine my H2O molecules sitting something like that, right? If we were to take a snapshot in time and they perfectly lined up to give us something like this, we can dissolve solid into here, right? Into these spaces. X's to not make it confusing. But it's compact. It's hard to really jam it in there, right? If we're hot, we have more particle motion. We're moving. Things are more spread out. It's easier to dissolve stuff. That's why warmer things have warmer liquids, in the case of what we're talking about, have a higher solubility, right? Gases, if you look back at that chart, the solubility of gas, right, goes down as temperature goes up. Because you start to hit a point where you're moving around so much, it's competing for space, right? So you hit a certain point with a gas, right? Which a gas is a higher energy state anyways, right? We've gone from a solid to a liquid to a gas. So those are bouncing around so much that it gets hard to put it in anything because it gets so hot. Right? It's the opposite of a liquid. So when we're talking about states of matter and temperature, the rules kind of change depending on what state of matter we're talking about. Just know that, right? Have that in the back of your mind, but know, at least for the lab that we did, that's why it works the way it does. It's because solubility increases as temperature increases. Okay. Does anybody have any questions? Do we understand the concept? Okay. We're going to start tackling some harder stuff next week. It's going to be a lot of practice. It's going to be a lot of practice with it, a lot of homework. Because it's a concept that we need to understand moving forward and how elements work with each other. Just know it goes deeper than even what we're going to touch on, okay? But we're going to start talking about filling molecular orbital shells. I gave you all a handout at one point in time that had the S shell, which is a ball, and the P shell, which is a dumbbell. Do you remember that? Some of you? We're going to talk about how those work. So we have valence electrons. They fill those spaces, and we're going to talk about how they fill those spaces, and the order they fill them in, and how we label things. Okay. So, that is all that I have to lecture on today. You guys have the rest of class to do